welcome back to this NPTEL online certification course in molecular rearrangement and reactive intermediates. In the last class, I started talking about the organosulfur chemistry. So I start about the different type of organosulfur compound. I introduce you to the thiol, then disulfite, sulfone, and then also the sulfoxide. And then I also talk about some of the important property of this different compounds and in some of the reactivity. In today's class, I am going to talk about, of course, some more about the organosulfur chemistry, and try to talk about some of the stabilized carbon ion using sulfur and some of the reactions. So first, I am going to talk about the sulfur stabilized carbon ion. Why the sulfur stabilized carbon ion, are whatever reactions are there, and why those carbon ions are formed, and what is their pK. We are going to discuss some of this. Then I think you must have heard about dithion. If you have talked about the protection of aldehydes, you must have seen the dithion protection. We are going to talk about that and the application. The Smith-TSA coupling, we are going to talk about this. And then the most important thing is the sulfonium and the sulfoxonium ylides. So these are the two important class you are going to see different type of reactions, and you must see also in the competitive exams the question comes from also these two important parts. And then I think we're going to talk about the stabilized and unstabilized version of these ylides, and we're going to see if you have a particular substrate, if you use a stabilized ylide, you get one set of product. If you use unstabilized ylide, you get another set of product. So first thing we want to start with this: the alpha carbon ion can be stabilized by sulfides, sulfoxides, and sulfone. So if you try to compare the pK of moving from a methane. Now if you replace what we are doing here, if you move from here to here, one of these hydrogen replaced by SPH. Now you can see the pK jump from 65 to 48. Okay. That means you can see slowly now what happened here from SPH. Now we move it to SOCH3. We replace one hydrogen of methane by SOCH3. Now pK jump to 35. SO2CH3, sulfone, then it is pK jump to 31. So you are seeing the acidity is slowly, and then now if you replace by one of this methyl by a phenyl, you can increase the even this proton become more acidic, pK 29. So what we are seeing, the effect, some sort of effect of sulfur we are clearly seeing here. Like of course once you from compared to the sulfur, once you go to the sulfoxide or the sulfone, what you are introducing, you are seeing that the electron withdrawing capacity of this sulfoxide or the sulfone, when it's sulfone, it is much more higher compared to this type of disulfide. Okay, so the stabilization is also getting increased. Because of the increased stabilization from going from the disulfide to sulfoxide to sulfone, what you are seeing that as the negative charge is getting more stabilized, the pK getting increased. So if you remember, if you talk about the acidity, then we always talk about that if the proton is more acidic, that means the corresponding conjugate base must be more stable. We are going to discuss them again, why these are more stable. We are going to come back to that also. And then there is another important factor is that once you are saying about this, there is a lot of studies was done about the structure of this type of carbon ion. So from some of the studies, it was found out that once you have this the carbon ion from a sulfone, so these are some sort of a planar shape. Means I am not talking about this part. I am talking about the CH2 minus. I am talking about that what we are saying here, that in this particular compound, the CH2 minus, correct. So once you have a CH3 here, of course once you have a CH3, what is the difference? So once you have a CH3, then this CH3, this carbon will have a sp3, correct, hybridization, and it's a pyramidal. But what you are saying that once it will become CH2 minus, this will achieve planarity. People have done some there are theoretical calculation, also some NMR studies. From there they found that from the carbon NMR studies, that this this corresponding carbon ion from the sulfone, okay, is actually a planar shape. Okay, but once you see about the carbon ion from a disulfide, this CH2 minus still having this carbon ion still having a pyramidal shape. And once you have something like a sulfoxide here, which is actually in between the sulfite and the sulfone, it is actually neither sp3 nor sp2, something in between. Okay. So now we are going to learn about some of the reactivity of these. Okay. So again, I think one of the other important thing about when you try to talk about the pK of methane versus you replace by SPH, we talk about a change of pK, correct, from 65 to 48. So one thing you might be clearly thinking, sir, maybe there is sulfur as a d orbital, carbon don't have it, or if you so because of sulfur d orbital, sir, when you have this CH2 minus, this might be giving electron density to the corresponding d orbital of sulfur. That's why it is getting stabilized. But the calculation suggested that that is not the major factor. The major factor is the stabilization of this corresponding sigma star. So if you see sulfur and a carbon having, so if this is a sigma bond between this carbon and sulfur, then there is a sigma star orbital here. So this sigma star orbital donation of electron density of CH2 minus non-bonding to the corresponding sigma star orbital is the most important reason about the stability of this type of corresponding PA corresponding carbon ion which is forming from this disulfide. Okay. So that is the important factor here, and one of the evidence also comes for, so you can think this type of dithion, we're going to come back and talk about them after a couple of slides. So in the dithion, if you have these two hydrogen here, one is your axial, one is your equatorial. Now if you try to compare their acidity, it is saying that the equatorial one, the one here, is more acidic than the axial one. So why the equatorial one is more acidic than the axial one? The evidence that in case of equatorial one, when it is forming the corresponding conjugate base, that means this corresponding carbon ion, this is giving electron density to this corresponding sigma star orbital. So this bond, carbon and sulfur, this is a sigma bond, so there must be a sigma star orbital here. So this sigma star orbital is getting electron density from this non-bonding orbital of this carbon ion. Okay, that's how this this corresponding conjugate base is getting more stabilized compared to the axial one. That's why the equatorial proton is more acidic than the axial one. Okay, so you can be, I think from these data you are convinced that in these cases, at the beginning when I talk about this methane versus pH SCH3, the stability coming from the electron donation from this non-bonding carbon ion electron to the sigma star orbital of the carbon sulfur bond. Now we are going to talk about the dim cell anion. Okay, dim cell anion is nothing but if you from a sulfoxide, if you are using a base like sodium hydride or the sodiumite, and I think then it can comfortably able to abstract. Of course, you can use n-butyl lithium also, that can able to abstract this proton from here to generate a corresponding carbon ion. It's called dim cell anion. Okay. So now again it can once you have this anion, you can think about that once this anion is formed, this can act as a nucleophile, because again this is a carbon ion is forming, so this can act as a nucleophile. So we are going to learn some of this reactivity of this dim cell anion. So once you have this dim cell anion, it can participate. You can see it is getting, it's a sulfur, it's a anion which is forming from the corresponding sulfoxide, correct. So we talk about that there is some sort of a stabilization, of course this through some sort of a resonance. Of course we said that it's not achieving a sp2 all the way, but again there will be some sort of a stabilization. So because of this, this type of this type of carbon ion is a stabilized one, can participate in SN2 reaction, okay, to get to this compound. So this is a simple SN2 product. So you can think about this is some sort of derivative of DMSO. So if you remember, I talked about in the last class, this is the structure of dimethyl sulfoxide. What is happening here? In the dimethyl sulfoxide, you are now changing this one of the methyl group to a butyl group, correct. That is what is done here. You forming a carbon ion and then going for a SN2. But now if you take this compound and then you heat up at high temperature, so then there is a thing is going to happen called a syn beta elimination, or it is called some sort of a EI mechanism, elimination internal or elimination intramolecular. Okay. So this is called as thermal scene elimination happening here. What is happening, you can think about this oxygen lone pair can take this proton, this can form this double bond here, and then this sulfur, the sulfoxide can get out, okay, to form the corresponding olefin. Again, there are different type of variety of this type of EI mechanism. It could be a 5 member, 6 member, or 4 member. In this particular case, you are seeing is going through a 5 member in the tangent state. If I try to draw, you will see is going through a 5 member tangent state, okay, to get to the after the elimination forming the corresponding terminal olefin. There is another example here. Instead of this, for the SN2, it can now the CH2 minus can attack to this corresponding ester to form this compound here. So you having this beta carbonyl in respect to the corresponding sulfoxide. Now if you have a potassium tarbidoxide, now you can think of think this type of compounds very similar to this 1,3 dicarbonyl compounds. So if you remember, I think in case of 1,3 dicarbonyl compound, this is the proton which is the most acidic proton because of the stabilization of this corresponding the negative charge which is forming there. So now for the corresponding carbon ion which is forming here, very similarly this is the proton which is getting acidic. So this is going to form in presence of a base, it is going to form the corresponding carbon ion. Again, this is a stabilized one going to perform a SN2 reaction, and then again the scene elimination able to generate this corresponding alpha beta unsaturated carbonyl compound. There is another option is after forming this compound, if you use the aluminum Ag, this can able to cleave this carbon sulfur bond, okay, to generate this ketone. From this stage also, if you able to do a the cleavage of this carbon sulfur bond using aluminum mercury, you can also able to get to the corresponding carbonyl compound as well. So dimsal anion act as a, so in the previous slide I show you it can act as a nucleophile. Here I am showing you that this can also act as a base. So this can act as a base to abstract proton from this corresponding. So this is a sulfonium, correct. So from this sulfonium iodide is a trimethyl sulfonium iodide, what you are generating a sulfonium ylide. So this is this proton from the methyl, because you can see it's next to a sulfur with positive charge. So you can understand that it's its pK is really acidic proton. So this can be abstracted by this dimsyl anion to generate the corresponding sulfonium ylide. We are going to talk about a lot about this reactivity of this sulfonium ylide. It can also generate sulfoxynium ylide. If you use the dimsyl anion, that can also abstract proton from the corresponding the sulfoxynium, and it can generate the corresponding sulfoxynium ylide. Okay. Again, we are going to come back to this and discuss, because you are going to see that in a minute. We are going to talk about that this is going to be a stabilized one, this is going to be unstabilized one, and there will be difference in the reactivity. Before going to that, we have some problem to discuss. So here we are talking about a problem that first because in the sulfur chemistry we have not talked about any problem yet, but here you can see in this particular compound, if you use a AgBA4 and so you have pH, SPH. So you can think about a disulfide here. So this can that the sulfur is sulfur is a better nucleophile, so going to participate in a SN2 reaction first, okay, to form this compound. So now what is going to happen after forming that the compound, you have sodium hydride, you treat it with sodium hydride. Now once you have a sodium hydride, if you think about the pK of different proton, then this is the proton which is next to a sulfur with a positive charge, correct. So this corresponding anion will be stabilized. So that's why sodium hydride can able to generate this corresponding carbon ion. Once it is going to form, it is going to participate in a SN2 reaction to generate corresponding cyclopropane. Now again, if you treat with the KOH here, then it can able to abstract proton from here. Again, this will be stabilized. This is going to form a ylide here, which is going to react with the corresponding carbonyl compound and generate. So we are going to talk about this this reaction, Korey-Czajkowski reaction. We are going to come back in a minute. So this can be this is a reaction between the sulfonium ylide and the carbonyl compound to generate epoxide. Further, once you forming this type of this is a epoxide and a cyclopropane, which of course is a strain molecule. That's why once you have a H plus, this is going to protonate the epoxide. There will be ring expansion happening to form the cyclobutane, and further the positive charge will be neutralized by formation of cyclobutanone. Okay, I think you understand first SN2, then there is a internal formation of the carbon ion, then again there is a internal SN2 type SN2 reactions, then the Korachakowski reaction, and finally there is a ring expansion to get to the product. So what will be the product in the following reaction? So if you look into the structure again, if you see, we are using sodium methoxide and methanol, so these are the base, and if you look into this molecule, you can see these are the the protons which are next to a sulfoxide, and these are allylic. Okay, so this can get stabilization on both the way. So this will generate this corresponding carbon ion first, and now this carbon ion is a stabilized carbon ion going to participate in a 1,4 addition here. Again, as I mentioned you that if you have a stabilized versus unstabilized, a stabilized going to go for 1,4 addition, a unstabilized going to go for a 1,2 addition. So that's why it's a 1,4 addition going to happen here. And finally, after the 1,4 addition, the ester is going to form this compound. The O minus will going to come back, and the double bond going to further come back, and so this enolate will come back and attack to get rid of the corresponding sulfoxide. Okay, to get to the corresponding cyclopropane. So now we are going to talk about some of the chemistry of dithion and Ampolang reactivity. Okay, I think you have heard about dithion before, and if you remember again, I think you have learned when you talk about the protection of aldehyde. So once you see protection of aldehyde using dithion, you have to use a Lewis acid for the synthesis of dithion to activate the carbonyl oxygen that can allow the sulfur to attack to the carbon, and then it will form the dithion. Okay, after the elimination of water. So now what is going to happen, that once you have a dithion, now if you have this proton here, again there is 2 sulfur there. So we already talked about in the previously, if you have seen that if you have a single sulfur, then this CH2 minus having pK around 48. Now if you have a 2 sulfur, you can understand the pK will be even lower. Okay, so you can, using a n-butyl lithium, you can comfortably able to go for this deprotonation. Okay, so now what is going to happen here, this is a stabilized organolithium which will going to participate in a SN2 reaction to form this compound, and then later what you can do, you can also able to deprotect and get to the corresponding ketone. Okay, the other things here that what you are saying about the the Umpolang reactivity here, because it's a electrophilic carbon at the beginning, so this carbonyl was electrophilic carbon. But once you make a dithion, okay, what is going to happen, this particular carbon in the dithion now become, you can able to generate a carbon ion here. So which was a electrophilic at the beginning, now become a nucleophilic carbon. Okay, so this type of reactivity is called Umpolang reactivity. Okay, again by using Umpolang reactivity, there are several different reactions developed. We are going to discuss some of this also. So this is, I think, the Umpolang. I think I should also include that Umpolang means actually reversal of polarity. So you see there is a polarity from electrophilic carbon, it is changing to a nucleophilic carbon. Okay, so then we are talking about, so we already talked about the the protection. Now we are talking about the how you remove them. What is the deprotection strategy of dithion? Now if you have seen that the dithions are more stable than the corresponding acetal. That's why dithions are more popular than acetal protection group, because you can use some of the other reaction condition, and if you have a mild acid, the dithions are still stable, but your acetals will be not stable. Acetal will be immediately converting to the corresponding aldehyde. So that's why you can see that there is a I think the dithion are more important and used for the natural product synthesis. So now the question is, what is happening here? Why the dithion is not getting hydrolyzed in presence of the acid? What is happening? What is the important thing is that once you have a H plus, the protonation of H plus. Now if you compare the electronegativity of sulfur and oxygen, which is more electronegative? If you remember, we have talked about electronegativity, and this is around 3.5 and this is 2.58, very close to a carbon. So if you see, if you put a if you give a acid And if there is a carbon CH3, do you think it is going to get, of course, if it is a very, very strong acid, otherwise it is very difficult that the methane will be, going to form, going to take the proton, correct? So if you think about the electronegativity wise, that's why sulfur, taking a proton to form SH, that, so this step is not very favorable step, okay. That's why what is going to happen, you will see a very low concentration of this which is forming. That's why majorly you will see the equilibrium is lying towards the starting material, okay. That's why the decomposition of this dithion is happening in a very less amount, okay. And even also, this is happening also, this can again come back to the original starting material. So that's why to stop that to stop, if it is forming here, can you able to take this compound and to something else, so and then get rid of this R from there. So that's from there the mercury playing a very important role, okay. That's why AgCl2 and then acid condition H2SO4 now can able to do the job to do the dithion deprotection to corresponding aldehyde group. So we trying to learn the mechanism of this reaction. Of course, the sulfur can act as a very good nucleophile, it's better than oxygen. So it will react with AgCl2 to form AgCl here with a positive charge on the sulfur. Now once you have a positive charge there, this can allow to open up this dithion to form this compound. So you can think that carbon sulfur double bond plus is some sort of a compound called thiol, okay, this type of compound. So now once you have this thiol, this can have a sulfur with a positive charge, now this H2O can attack here, okay. Or you can also say this is a sulfonium type things, because we have learned that once you have a sulfur with 3-methyl or plus, we call this as a sulfonium. So now the water can attack here to this carbon sulfur double bond then it is going to form this compound. Again the sulfur is free here, so sulfur can attack to the mercury to get it of, because sulfurs are very good nucleophile. It will attack there to get rid of this corresponding chlorine to form this very important compound. It is called the cyclic mercury dithiolate. Once it is forming this sulfur with a positive charge, now this it's going to get form the corresponding aldehyde and get rid of this cyclic mercury dithiolate. So sulfur is kind of getting out and this RCHO coming out. So that's why this reaction is irreversible. This cannot go back to the starting material. That's why mercury chloride playing a very important role for this deprotection. Again, if there is another approach, if you have a dithion, you do first oxidation with periodate to form the sulfoxide. Once you have a sulfoxide, now you can able to use a H plus, because now oxygen can get protonated. And once oxygen protonated, that will allow the rupture of this dithion ring. And then further, if you use the H2O, it can able to get to the corresponding aldehyde. Again, I think the dithions are acyl anion equivalents, okay, and it can useful for the synthesis of acylsilane. I think I talk about this compound in the Brook rearrangement. If you remember that if you have we are talking about some sort of a acylsilane, means you have, this is the functional group we are talking about, a CO with TMS. Okay. So this type of compound synthesis can be done using this dithion protection. So you started from aldehyde, so we started from corresponding aldehyde. This hydrogen was replaced by a silicon. So I think this is a trimethylsilane. So this group was introduced by replacing H. So this is done how? You first do a dithion protection, okay, and then there is a reversal of polarity. So umpalang, so n-butyl lithium can generate the carbon ion, which is stabilized, react with TMS chloride. The TMS chloride structure is this. So it can react here. Again, I think if you remember, this is again some sort of SN2 with a silicon. So you remember that is forming some sort of a pentavalent silicon species. Then at the end, this chlorine will get out to form this corresponding compound here. Now once you treat with I2 and calcium carbonate, okay, again this I2 calcium carbonate is another reagent which can be also useful to the break this dithion ring here to convert to the corresponding carbonyl. Okay. Again here I think if you understand what we are doing here, we are converting the sulfur, because sulfur is a good nucleophile, so it will form sulfur iodine bonds, which will be allowing them to cleave the dithion. So sulfur will be positive. So what is happening here? You are forming sulfur with iodo, that will be positive sulfur, that will allow you to open up. Once this is open up, you have waters and you have calcium carbonate that can do the rest of the job to get to here. Okay. Because the thing is, you are not using a very much harsh condition, because if you have a harsh condition, then this acyl sealant, like the one we have shown here, the mercury chloride, and this condition cannot be used here, because that can destroy the corresponding acyl sealant. Okay, that's why you have to use a milder condition to open up. Again, here what we are seeing, there is another example here. You have this the 2 benzaldehyde, 2 COH group. First there is a protection, dithion protection, then N-butyl lithium going to form this corresponding lithium. You have this, so there is a 2 benzylic bromide group here. So there is a they are 1-2 position, so that they can react, form this cyclic compounds here, and then first you will be the deprotection from here. Once you form this compound, AgCl2 can form this corresponding carbonyl compound after the deprotection. Or if you use a ranitidine, okay, the ranitidine can do one thing, they can cleave this carbon sulfur bond and give you a carbon hydrogen bond, generate a carbon hydrogen bond using this H2 gas, okay, that can able to generate this compound. So now we are going to talk about the Smith-THA coupling. I think, as I told you, that there are very important reactions because of this Umpolang reactivity. So this is a one-pot and multi-component coupling of 2 silylated 1,3-diene with epoxide. So what it is doing, actually at the beginning, it is forming a silylated 1,3-dithion. So we are talking about a particular class of 1,3-dithion. So this is not going to happen with any dithion. This reaction is limited. We are talking about a silylated 1,3-dithion, means we are talking about a compound. The dithion will be starting from a aldehyde, and then we are talking about there will be a SiR3. So you can think about that you started with a acyl silane. So you take a acyl silane and then do a dithion protection. So you have, as I mentioned, that you first make the dithion protection, and then once you have that compound, now you can use for this reaction. Okay. So here what is going to happen here, or there is another option, you can also start with this dithion. Okay, you can start with the dithion and then generate a carbon ion and then react with the TMS chloride, that can also comfortably generate this compound. So once you have the starting material, you treat with N-butyl lithium, that can this will be Umpolang and generate a corresponding lithium here. The lithium can attack to the epoxide and it will attack to the corresponding terminal position. Once it is going to attack the terminal position, it will going to form this compound. Now if you remember, your R1 is actually silicon. So if your R1 is actually SiR3. So what is going to happen? If you remember, we talk about this 1,4-Brook rearrangement. Okay, so that means this O minus is going to take the silicon, generate another lithium, another Umpolang going to happen here, you generate this lithium again here. So if that is going to generate, that is going to react with another batch of epoxide going to react here. Okay. So now if you have this 1,5 polyol fragment, because you are generating a 2 hydroxy group in the 1 and 5 position, and you have a carbonyl group in the 3 position. So which can be it can be deprotection of this dithion can generate corresponding carbonyl compound. Okay. So now if you can able to do the reduction rate, then you can generate 1,3,5 triol, or if you can able to get rid of the carbonyl group, you can introduce a CH2 group. Okay, by some sort of Wolff-Kissner reduction. So now we are talking about the Smith-THA protocol. The Smith protocol is a useful the synthesis for unsymmetrical enantiomer 1,5-diol using the 2 different epoxide. Okay. So first I talk about, in the previous slide, if you see, this is the protocol which was a THA protocol. There what they are doing, they are actually using a C2 symmetrical enantiomer 1,5-diol, and here the same epoxide actually reacting 2 times. But in case of the Smith group, the Amos Smith actually developed this protocol, used HMPU or DMPU as a additive in the solvent, which significantly increased the rate of the reaction, and that allowed the 2 different epoxide to be coupled. That is the important thing. Once you use them, now what Smith group is doing, first there is a 1 epoxide forming this, and then the first Brugge rearrangement is happening, and then they are introducing the second epoxide into the reaction. By controlling the equivalent of epoxide, they can able to react and using the additives. Okay, that is very important. The additives playing a very important role to stabilize the corresponding lithium, which can now react with another epoxide. Now you can make this 1,5 polyol fragment which are unsymmetrical. So if you need a 1,5 polyol is a symmetrical same epoxide, then you can use the TAJ protocol, and the other case you use the Smith protocol. Mechanism here again for the prolonged reactivity, generation of lithium attacking to the epoxide. Okay, then the 1,4 Brugge rearrangement, and now the HMP again going to stabilize this corresponding lithium, which can react with another epoxide to get to the unsymmetrical fragments. And there are some synthetic application here. First again the T-butyl lithium can able to be put it with TBS here, attacking to the epoxide. 1,4 Brugge rearrangement here, generation of the corresponding lithium attacking. So now you are attacking in the both the site. So one equivalent of this can attack to the both of these site to generate. So now you can see how can we control the multiple so it's a polyhydroxy fragment. You can able to control the stereochemistry. So you can get a very high stereoselective product. Okay. And that can be used for the Skybar C16 to C28 sectonite sub-target synthesis for the mycoticin A and B. So this is the natural product, and this is the particular fragment which was synthesized using the Smith TAJ coupling protocol. Again sulfonium salt and the sulfonium ylides, I think we already talked about that. If you have this dimethyl sulfide, these are nucleophilic, attack go for SN2 reaction to generate trimethyl sulfonium iodide, and if you use a butyl lithium or sodium hydride, then these protons are this proton acidic, can be abstracted, generate corresponding dimethyl sulfonium methylite. Okay. So now you can use them. So again there is no sort of a stabilizing group here, so these are not very stabilized halide. But in this synthesis there is one problem. The problem is the first step when you treat with methyl iodide, you are forming this trimethyl sulfonium iodide, correct? So you have a I minus that can also attach to the methyl to get back to the, so this reaction will have some reversibility. To stop that, if you can use the Marvin salt, which is this compound, then you don't have this problem. Okay. Now that can take a methyl group, okay, and you have a dimethyl ether and this BF4 minus, so there is no way to get back to the starting material, which can be comfortably now able to generate the dimethyl sulfonium methyl. Okay. Again, once you have this, so we talk about now we are talking about the sulfoxynium salt. So you can think about DMSO, you can able to do the resonance structure putting sulfur plus, because if you remember if you try to draw DMSO, one thing you should always think about it, the electronegativity of sulfur and oxygen, 3.5 versus 2.58. I am telling you again and again, because what that is telling you that all the electron density is actually lying on the oxygen, not on the sulfur. So you can write comfortably this structure that O minus S plus. Okay. So now if you think about that, then you can think that that O minus and then the S plus. So then now you can, if you treat with the methyl iodide, you can able to generate this trimethyl sulfoxynium iodide. Okay. Again your the sulfur can be reacted with the methyl iodide to generate this corresponding sulfoxynium iodide, and now you can use N-butyl lithium to able to abstract this proton to generate this I already talked about the dimethyl carbanion or dimethyl sulfoxynium methylite. Again this is a stabilized halide because you have this SO group to stabilize this corresponding carbanion. So these are called unstabilized because there is no stabilizing group, but once you have a SO, I am going to bring back to SO2 based carbon ion. I'm going to come back to that. Or if you have some sort of a stabilizing group like cyano or ester, these are called stabilized halide. So there is a difference between the stabilized and the unstabilized halide. Now once you think about the reaction of carbonyl compound, you know what is going to happen once you have, once you reacting with this one versus this one, the sulfonium versus sulfoxonium halide. So one is stabilized, one is, so if you have an unstabilized, then it will go for 1,2 addition. Okay, this is the bottom line here. So 1,2 addition going to happen. First there will be, so if you see about the mechanism what is happening here, first there is a 1,2 addition, formation of O minus, and then you have this S Me2 plus, so O minus going to come back and get rid of this to generate corresponding epoxide. Okay. So from carbonyl compound you can comfortably generate corresponding epoxide, but again the stabilized halide also can do the same job, because there is there is no 1,4 addition possibility, so it will go for the 1,2 addition. But as soon as a possibility of, so as soon as you come to enones, then there is a possibility of 1,2 versus 1,4. So stabilized the halide will go for a 1,4 addition, so attacking here, and then it will going to come back, so you end up generating this sort of enolide intermediate where you have CH2 and you have SO Me plus. So this can come back here and get rid of this. Okay, that can generate the corresponding cyclopropane here. And here, if in case of unstabilized halide, it will directly go for 1,2 addition to generate the epoxide. Okay, so 1,2 addition of halide to an enone is a very fast reaction. Okay, what they are saying, the reaction is a very fast reaction, but in case of unstable halide, this reaction is irreversible in nature. That means this is a kinetic control product. So once you have unstable halide, this is the first and irreversible going to the product, and it is no way to come back. And then this is the conjugate addition will be a slower reaction. Okay, because this is going to be a the thermodynamic control one. But now once you come to stabilized halide, what they are saying, in case of stabilized halide, this 1,2 addition can happen, but this reaction is a fast and reversible. That means once this is forming, this can also come back, this can come back to the starting material. So in that case, the slow addition, the other one, which is the 1,4 addition, is actually slow but irreversible to give you to the thermodynamically controlled product. So that's why what is going to happen, again there is another thing you can compare, that this is a softer, so this is a soft nucleophile and this is a softer position. So that's why the 1,4 addition going to be preferable here, and it is going to end up giving you the thermodynamically controlled product. So in this part I talk about sulfur stabilized carbon ion, I talk about what is the reason for their stabilization, I talk about the non-bonding to the sigma star electron donation, I talk about dithion, Smith-TJ coupling. There are several things, can be symmetrical, can be unsymmetrical polyols, sulfonium salt and sulfonium halide, sulfoxonium halide and salt generation, and also I talk about their reactivity difference. The references, of course you can get lot more about this chemistry from this Jonathan Clayden books. Again thank you so much for coming to the class, and I am going to see you guys in the next class. Thank you.